Hello and welcome to my Physics 2211 Lab 5 Video Lab Report, Choose Your Own Adventure. So a quick overview of the lab. We're tracking the motion of a system involving two moving masses with collisions involved. We'll see that in a moment. Fundamental principles in play is Newton's second law, which relates the net force of a system to the change in momentum per time. And the electronic tools used were a tracker, close grip, and a recording camera. So a few important starting equations. Momentum is defined as the product of a system's velocity and its mass, shown here in vector form. The average velocity is defined by the displacement per time, shown here, and with some algebraic manipulation we can get this position update formula, which we'll use in the model. So the power of Newton's second law is that it relates the rate of change of a system's velocity over a certain time interval to the ratio of the total net force acting on the system to the system's mass. So some algebra, we can get a few important implications: velocity update formula, which we use in the model, and the momentum principle, which we saw earlier. The magnitude of the force of gravity of an object defined as the product of system mass and the constant g, and it's in the direction in the negative y direction, so this is in vector form. And for the drag force, we say it's proportional to some constant b to the system's speed, and the direction is opposite that of velocity. So therefore, for the purpose of the lab, this is the drag form in vector form as well, and b was chosen through repetitive testing. So using Newton's second law, or the momentum principle, and the implication of conservation of momentum for a closed system, the goal of this lab is to use a computer model to predict the observed motion of two interacting objects split over 4 intervals. So let's look at the video now, and we use a few things, so the tennis ball we use and everything else, and the orientation, calibration, and frame rate were set. So here is the actual motion we are trying to model. As you can see, we have two tennis balls, and they each interact a bit with each other with multiple collisions in their surroundings, and they end up about the same height. So this is what we're trying to model with our code. So a few initial conditions: we have the masses of the object, the time, the gravitational constant, the j hat, which is the direction vector, and the proportionality constant for drag. So for the first loop, we have the initial positions for the tennis ball, the ladder, and the pillow we saw, and they're put in vector form, and this was an estimated throw force that I had using some analysis of the system itself. So predicting the motion, we have the forces of gravity, throw, and drag on the first ball, because that is the only thing moving initially. Then we use the velocity and position update formulas, and then we update the graphs, which we will see later on as well. So for the second loop, this is right after the two balls have collided and energy is transferred between them, and using some concepts between the momentum principle and the conservation of momentum, we can find that the second velocity was approximated to be this, and then we set the positions and the x and y coordinates for the tennis balls, because everything else has not moved, and we have put them in vector form. So for predicting the motion of it, we use about the same process, but now we model each ball moving. So we have the force of gravity and drag for both balls, shown here, and then the velocity and position update formulas as well. So now the first ball actually hits the ladder, and then we estimate the magnitude and the direction for the force to match the motion, which is another assumption we had to make, and then we do the same thing. And the reason we have this if-else statement here is because it only applies that force for 0.001 second, which imitates it being applied over that time interval, which we use for Newton's second law, and then we use the same loop as before. And finally, we have the pillow force acting on only the second ball, which uses an estimation as well, shown here for the impact force, and direction we assume it to be straight up. And then we have the velocity position update formulas, again for both balls. So let's look at the model now. Here's it running. So here we can see the ladder, here we can see the ladder, the pillow, and both of the tennis balls. So here is just about after the first collision. And then it will hit the ladder itself. And we will take a look at these graphs shown below momentarily, but for now we're just looking at the motion. So then the first ball goes back up in the air, and the second one falls to hit the pillow. As you can see there, only the force of drag and the force of gravity are acting on these two for all this time. And then the second ball hits the pillow, loses energy, goes back up until it just about hits the peak of motion. At the same time, the first ball is still falling until they reach about the same height, which is nearly what we were trying to show in the model itself. So we can take a look at the graph comparison So here's the experimental and model comparisons for the x and y directions. The x were about the same shape, but not necessarily the same values. Y matched pretty closely. Same thing for the second ball. X were about the same shape, not super great match, but the y value was much better. And we see the velocity analysis for the first ball. We can look at where the forces were applied. It changes the velocity. And the same thing for the second ball, not moving to not. So some possible sources of error. I had to assume that there was constant gravitational acceleration, all interacting forces I had to assume, and the types of collision being elastic. And possible sources of error were the position variance for me putting in tracker, inconsistent surface area of the ball for drag, and internal energy changes. Thank you for listening to my video.